Today's lecture is about Hess's law. It's the one of the more practical applications of thermodynamics for understanding chemical reactivity and chemical reactions. The the basis of Hess's law is simply the fact that the enthalpy, or rather any thermodynamic state function, is a state function, which means, as we discussed the last time, a state function is any thermodynamic function that only depends upon the current state of the system. And the beauty of writing things in terms of state functions is that going from one state function to another state function, it gives you a change in the energy or something like that. Change in the enthalpy, for example, does not depend upon how you go about that particular change. Enthalpy is one of these central concepts, and actually any state function is a central concept in thermodynamics. So it's again important to understand what an enthalpy is, and why I keep emphasizing this issue of a state function. The enthalpy, as I've written out over on the slide, is the enthalpy denoted H is equal to the total energy of the system plus pressure volume. And the way you can think about this is that this is the total energy. Required to create the system. And this pressure volume is the pressure volume work of expansion, to expand environment to accommodate the system. So in other words, it's like if I have this tank of water over here and I create a little cavity inside of it, I had to push stuff out of the way to create my thermodynamic system, which I'll denote as this little blue blob here. Here's my thermodynamic system. Now that is a total amount of energy, and I had to push the environment out of the way to create that. And again, it's a state function, and the way we arrive at the state function is first of all, it's important to understand. These are not simply arbitrary definitions that we impose. That E is the total energy of the system. Pressure volume is the work required to expand the system. And what does that then give us a measure of? Well, to see any thermodynamic quantity, you really can't measure directly. In fact, it's impossible to measure directly the total energy of a system. And the reason for that is, as I'll explain in the next in a sketch in a moment, is that it's there are many degrees of freedom, things that go into this, and it really is sort of an irrelevant question. What is the total energy of the system? More importantly, it's the change in the total energy. And so what is the change in the enthalpy? What is the change in this total energy plus work to expand the environment to accommodate the system correspond to? So again, we'll denote this as a differential, a total derivative, or total differential in this case, dH, which again is the infinitesimal change in the enthalpy, as dE plus dPV. Okay. Now again, we use our definitions from this is heat minus PV dV. Now we're going to add plus dPV, and now let's work this out correctly. Q minus P dV plus P dV minus VdP. Because if you remember how you take derivatives of a composite function, let me just remind you up here. So the derivative with respect to x of f of x times g of x is equal to the first times the derivative of the second plus the second times the derivative of the first. Right? So this is just the distributive law of how this linear operator dx acts upon those two systems. So we do the same trick down here. It's just as simply looking at just the d part, if you would, of the top part of the differential and evaluating all of this out. So again, this is now equal to Q plus VdP. Okay, and at constant pressure, dP is equal to 0 at constant pressure, so I'm left with only the measure of the heat. Remember, heat, Q, is the heat added to the system. Q is heat added to the system. So if I look at the heat added to the system, I get the enthalpy. I get the change in the enthalpy. And that's what we do with calorimetry. Okay, that's just a recap of what we talked about the last time. So remember that. Okay. Now, next slide. So, Hess's law is quite easy to understand. And basically, in Hess's law, I have that the enthalpy of a reaction is equal to the enthalpy of a reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. But one of the things that isn't necessarily obvious in this is that, let's say, for example, I have a set of reactants here. Now, I don't know, and it has a given enthalpy. I'm going to draw this as a diagram. Here's an enthalpy. If I could measure, here's my reactant. Maybe it's A plus B. And I'm going to look at some sort of reaction. Of my total reaction is going to be something like A plus B goes to, let's say, something simple like C. Okay. Okay. Now, C is some sort of enthalpy. Now, I don't know what C is, and it really doesn't matter in terms of this. But let's say I don't know. I've never done this reaction right here. I want to find out, or I want to estimate what is the enthalpy of this reaction. How much heat is liberated or is required to create C from reactants A plus B. Well, maybe I don't know this, but maybe I know that maybe D. Maybe I know something that goes like this. Maybe I get something that looks like that. Maybe let's say that C, D plus C gives me something, I don't know, let's call it E, okay? And maybe I know, and I have the delta H for this is, I don't know, maybe this has a delta H is known, but maybe what I know is something that goes like, I create something and I have a series of intermediate steps. Okay, maybe I have a series of intermediate steps and I finally get to C. And these are all intermediate steps that may or may not be, may or may not exist. So it's like, for example, let's say I was looking at this reaction that I have over here to the side of N2 in the gas phase, and now state is absolutely incredibly important to keep track of, because there's an enthalpy that's associated with vaporization, and enthalpy that's associated with all sorts of different kinds of things. So this would be some intermediate state, an intermediate state, and then finally C. This is our final delta H that I want to know. Now, is this a endothermic or exothermic reaction? Just to quickly recap, this is going to be an endothermic reaction because it's going to require heat, a net amount of heat, to create C through this pathway. Now, if I go a different pathway, it will still be the same delta H. It doesn't matter on the pathway. Delta H is a change in the state function. This is has an enthalpy of C. This is the enthalpy of this. Irrespective of how I go about this pathway, I will always have this particular reaction. Okay, this particular state. Now, in this particular case, we're looking at plus 2 O2 again in the gas phase, and I want to create 2 NO, 2 in the gas phase. Okay, now the oxidation of this this is the oxidation of N2 to form nitrous oxide. Okay, now one of the things I don't know, maybe this is one of the things I can do. I can look at, well, I can break this down into two kinds of steps. I can say that N2 in the gas phase plus 1 molecule of O2 in the gas phase gives me 2N2, 2NO in the gas phase. Okay, and that has a delta H that's equal to, according to 180 kilojoules. Now, one of the things that's important to note is that this is per mole. Okay, these are all molar quantities. So if I have 1 mole of this plus 1 mole of that to produce 2 moles of this requires 180 kilojoules. Okay, so that's important to keep in mind, that this particular reaction is per molars. This is for these stoichiometric coefficients in molar quantities give you 180 kilojoules per mole, or require 180 kilojoules per mole of enthalpy to create this in this quantity. Okay, so and then the next thing I can do is that 2NO in the gas phase plus 2O2 also in the gas phase gives me 2NO2 in the gas phase. Okay, and this has a delta H of minus 112 kilojoules. Slide it over so you can see that. Okay, it's also what's written on the other side. Now, if I add these two together, you see the net reaction of this. The net reaction is the reaction I want. See the net reaction. See this. This net reaction. Oh, this is only one. Sorry about that. There's only one of those guys. There's a net reaction. So 2 moles or 2 molecules of that appeared over here. 2 molecules of that appeared over here. I can add these guys together, N2 in the gas phase plus O2 in the gas phase to give me 2 NO2 also in the gas phase. And I can simply add these two numbers together and get 68 kilojoules, because this is negative, and I add these two guys together. Delta H, this plus delta H of that is a 68 kilojoules per mole, or 68 kilojoules for my delta H. Okay, so in other words, if I take 1 mole N2 gas, 1 mole O2 gas, I get 2 moles of 2N2 gas, and it cost me 68 kilojoules to do that particular reaction. Now, it's important again to keep in mind that this is a quantity dependent number. If I double the moles. If I had 2 moles here and 2 moles of this to get 4 moles, it would require twice this, right? 136 kilojoules, right? Because if I instead had the reaction where I had 2 moles N2 gas plus 2 moles O2 gas to give me 4 moles NO2 gas. Well, see, this is really twice that reaction, right? I multiplied all those by 2, and so the delta H for this reaction is now equal to 136 kilojoules. Double that number. So the point being is you need to keep track of, so each reaction, the number that you get here will depend upon the stoichiometric coefficients that we have. Now, to make life a little bit easier, we tend to tabulate this in terms of a per mole. So for example, if I were to write the delta H of this reaction in terms of a per mole of that reaction, let me write this up here. So per mole of N2 NO2 gas, get rid of this, I would have half that number, right? It's 34 kilojoules per mole is the delta H to produce per mole on a per molar basis. Now, some books will denote the molar quantities in different ways. I like to put a little hat on the top of this to denote this is a molar quantity. Now, I'm emphasizing that this is an amount dependent quantity. Most quantities in thermodynamics, or many quantities in thermodynamics, are what are called extensive quantities. And since we haven't introduced that term, I'm going to do so now. In thermodynamics, we have intensive versus extensive quantities. Okay? And intensive quantity is something that does not depend upon the size of the system. So intensive does not depend upon size. For example, temperature. The temperature of this object right here, this nice little parallel rule that I have made out of brass, okay, doesn't depend upon the size of the system. If I double the size of that ruler, it's still at the same temperature. Internal energy just doubled, so I have twice as much volume, twice as much stuff. Pressure doesn't depend upon the size of the system, right? Pressure does not depend upon the size of the system. Those are intensive variables. Pressure doesn't depend upon the size of the system. Temperature does not depend upon the size of the system. Extensive depends upon the size of the system. Extent. Okay, think extent. How big is the system? Volume is the size of the system, right? The energy depends upon the size of the system. Enthalpy depends upon the size of the system. All sorts of quantities depend upon the size of the system. Temperature and pressure do not. Energy, volume, entropy, which we'll discuss next, enthalpy depend upon the size of the system. So consequently, all of these reactions have to be scaled according to the number of moles that they produce, and to get this into a useful quantity. So a lot of times we're going to see chemical reactions with maybe fractional stoichiometric coefficients because we want to produce 1 mole of the desired reaction, of the desired product in this particular reaction. We'll see this. That's okay. Only thing I need to do is double or halve or multiply the final delta H in order to get the stoichiometric coefficient quantity that I need for that particular reaction. It's okay to do that because enthalpy is an extensive quantity. Okay. Now that allows us to do, for example, a multitude of different kinds of pathways. So what I have written out over here is this particular pathway that we just worked through. We start off with N2 gas and two O2 gases. Now these are in general, it depends upon the pressure, it depends upon the state of the system, but they're in some thermodynamic state. If they happen to be at a standard state, then I could say, well, I have a standard enthalpy for N2 gas, a standard enthalpy for 2O2 gas, and if I do this first reaction, I require so much energy. So here I have O2 gas and 2N2 gas. So I start off with 3 moles of molecules on here and 3 moles of molecules here. It's just that I rearrange these into O2 gas and 2 NOs, and then we take this guy and allow this reaction to occur, and this is favorable thermodynamically, minus 112 kilojoules to get down to here. Now it doesn't matter how I go about this particular reaction. The enthalpy of 2 NO2 molecules, or 2 moles of NO2 molecules, is the same irrespective of how I happen to get to that point. So I can do the long way, or I can maybe do a short way. It doesn't matter. If I go back down to the initial reactions, I get a negative delta H. This is the reverse of this reaction. If I go forward, I get a positive, and I get a negative. Now, again, you need to keep track of the sign of delta H and the sign of all this. Did I run the reaction forward, or did I run the reaction backwards? So, for example, if I were to say, what is the enthalpy of the reaction of 2 NO2 gas molecules to go back to N2 plus 2 oxygen molecules, it would be the negative in this number. I would go down by 68 kilojoules. Okay. If I wanted to do this in a molar quantity, I would go down. So if I took 1 mole of N2 gas, NO2 gas rather, and do the reaction backwards, it would be negative 34 kilojoules per mole of NO2 gas. Okay, so again, another example. We can work through this. We can see this. We'll see how this comes about by watching very carefully. Okay, it's almost easier just to follow along on the PowerPoint rather than my handwritten notes, because I'm simply going to write down again what's on the PowerPoint. So this is a possible rocket fuel. So we would hope that the combustion of this is going to be something that liberates a lot of energy, and we're going to create it by taking boron from its constituent components. We're going to basically make this molecule from the constituent components: boron, solid phase, hydrogen in the gas phase, go directly to here. That's actually not the way you do this reaction, but let's just work out the thermodynamics. So in other words, the key quantity, if you want to think about it, what would be the decomposition of boron hydrate back to its elemental constituents in their reference or standard state? So hydrogen in its standard state is a gas. Boron in its standard state is a solid. So maybe we could look at the decomposition, or we could look at the composition reaction. It doesn't matter. It's because enthalpy is a state function. If I go forward, I get one quantity. If I go backward, I get the opposite quantity, the negative of that number. Okay, so to see how this works, so let's say I've never done this particular chemical reaction before, and I want to know how much energy, how much enthalpy is going to be required to create boron hydrate, diborane rather. Okay, so but I do know this. So if I make 1 mole boron oxide. So oxidized boron plus, again, it was like, why I get 2/3? Well, because I want to get this in a per mole. So per mole of this quantity. Now, I could, if you wish, I could balance this out to make all of these nice integer stoichiometric coefficients. It would take 4 of this plus 3 of this to give me 2. But if I want to know what this delta H is per mole of this molecule, let's just write it. It's okay. We can make these stoichiometric coefficients fractional. It's not a problem. It's the same chemical reaction, except that this delta H is per mole of this quantity. Okay. Now this stuff, if I react backwards, or if I can react it with water to form our diborane, which is what we're looking for. This is sort of the backward reaction, right? So this is like going in reverse, and I also can create water. This is the water reaction to go from water from its elemental components. This, if you want, this is the enthalpy of formation of liquid water from its components. So again, hydrogen gas, oxygen gas to liquid water. That's what the L means, is minus 286 kilojoules. So if you want, the enthalpy of formation of liquid water is 286 kilojoules per mole of liquid water that I produce. And it would require 1 mole of hydrogen and half of a mole of oxygen to do that. Again, and then this last reaction isn't so much a chemical reaction, but I need to keep track of it because I need to make sure that I have the phases, the liquid phase versus gas phase correct, because all of this is gas phase, and water is created in its standard state in the liquid phase. So I need to vaporize liquid water to gaseous water, and that requires 44 kilojoules per mole of liquid water to produce 1 mole of gaseous water. Okay, so again, all of these are done in quantities reflecting per mole of what, for example, this is minus 235 kilojoules per mole of this quantity that's produced. Now that's important to keep track of that, and because what we're going to do is we want to find the delta H for the total reaction. I'm going to look at these different reactions and rearrange so that the net reaction, maybe I'll run one reaction forward, maybe one reaction backwards, but the net reaction will be the final reaction that we want to do. And so a way to do this is sort of to work backwards in a lot of ways. And if you run a reaction backwards, just change the sign of delta H. And if you need to multiply a stoichiometric coefficient, you multiply that stoichiometric coefficient by whatever you did to that delta H. So you have to sort of play around with various combinations of the reaction in order to get the final reaction to be what you want. So that's what we'll do. So let's do the first step. So if I take boron plus oxygen to form this boron oxide, so I can oxidize this to get solid, and that's this reaction, and then add water to this, I get the reactant that I want. But you see, I also get oxygens all over the place. So the net reaction, so in other words, if I could do this, this would liberate a lot of energy, 1,273 kilojoules per mole of this that's produced. Now if I react this quantity with 3 moles of water, I get a net reaction. You see, I can cancel out some oxygens over here, some oxygens over here. And if I take the sum of these two equations, here from that, this from that, here from there, some water, I get 3 oxygens coming off on this side, I get 3 halves oxygens on this side, and so on. I can start deleting things and cleaning things up a little bit. So 2 borons, 3 waters gives me this reaction. That's the net of this reaction. Now notice this is water in the gas phase and I have 3 halves O2. Okay, so now I need to clean things up. I'm going to remove the O2 and these two and introduce H2 gas as a reactant. So that's not quite the reaction I want. So the reaction I want is this, boron plus hydrogen. And here I have boron plus water. That's not the reaction that I would want. We need to clean up this water and this oxygen over here. So I need to get back to my original reaction by getting rid of some things. So how do I do that? I have the product I want, but now I need to clean it up a little bit. So I can do that by removing by the water reaction. So the first thing I can do is the hydrogen plus oxygen gives me a water. That gets rid of 3 of those guys. So if I have 3 of these things, I can now add these things together. So I add all of these guys together. But I want to see the reason I want to do this is that if I have 3 waters over here and 3 waters, wow, but look at this. This is 3 liquid waters, and that's like 3 gaseous waters. It hasn't quite gotten rid of this. The oxygens are taken care of because I can get rid of that 3 halves oxygen and that 3 halves oxygen, but I can't get rid of this three water liquid. There's 3 liquid waters over here and 3 gaseous waters over here. So we're not quite done. We have almost everything that we need. We have 2 borons, we have our 3 hydrogens, we have our diborane here, but we have we can get rid of this guy, we can get rid of this guy, but we're not quite done. So what we need to do is vaporize, or rather, we need to vaporize the water. Again, this is the water vaporization reaction, and now I have the net reaction that I want, where I have all of these things going together. So it's a little bit of a multi-step strategy to solve these kinds of problems. You have to play around with different scenarios, if you would. Play around with different pathways. Look at the information that you're given, look at the pathway that you're given, and piece these together to form the final reaction. It simply just takes practice, I will say. It simply takes practice looking at how to do that. So do the problem sets. Again, I can work through multiple examples, and they're all the same. It almost seems like magic the way these things come about, but it is. It's simply because you have to look at the different pieces of information that you're given and add and subtract those pieces of information to get the final reaction that you want. And again, to keep track of the particular thermodynamic phase of the system, because that matters. You notice in this particular case, if I didn't, and this is a lot of energy, so I went from minus 96 kilojoules to plus 36 kilojoules because of this issue of the vaporization of the water. So that's important. Now again, you need to work backwards from the required reaction, using both reactants and products, and decide how to manipulate the different reaction steps or reaction components that you're given. You can reverse things, you can multiply things through by stoichiometric coefficients, and use that to build up, if you want, a pathway to go from your reactants to the products. Now, again, why does this all work? And it's because enthalpy is a state function. Enthalpy is a state function. It does not depend upon the change in enthalpy does not depend upon the pathway. I can pick different pathways and I will get the same delta H. Now, one of the things that I've been mentioning a couple times through this, again, thinking about delta H or H itself, it's the energy required to create the system plus expand the system for it to occupy space. You need to push the environment out of the way. Now, there are standard reference states that we use for tabulating thermodynamic information. In the Handbook of Chemical Physics, or Handbook of Chemistry and Physics rather, you will find tables and tables and tables of enthalpies of formations of different chemical compounds and so on, and with that chemical, and with and as well as the standard state of that particular compound. What that standard state means, it is the change in enthalpy required to create 1 mole of substance and push the environment out of the way to as well. So and that standard state. So again, let me reiterate this. So enthalpy, if you want it, the enthalpy of formation, the delta H of formation, and there's all sorts of different ways that we can denote this. So delta H of F is what's denoted here in the notes, is the delta H enthalpy of formation. Remember what enthalpy is. I have the environment. I need to create the system. I create 1 mole of let's say, NH3 gas from its constituent components, and I push the environment out of the way. So in that little pocket, I did the reaction of N2 plus H2, all in the gas phase. In this case, I'm going to use to give me NH3. So I'm going to need to have a half of a mole of this guy and 3/2 moles of that will do it, I believe. And that delta H, so at standard temperature and pressure, which I'll denote S, standard temperature and pressure, okay, the delta H of formation, and that little 0 here denotes standard temperature pressure. What is the standard temperature pressure? Is at T equals 298.15 Kelvin, and the pressure 1 atmosphere. In other words, this is 25 degrees Celsius and 1 atmosphere of pressure. So why these particular quantities? Well, those are pretty much the standard laboratory conditions for a system. So you have a pressure of 1 atmosphere pushing down on the system, and at temperature T, I create space for 1 mole of this stuff in the gas phase. These are all in the gas phase, by the way. And that delta H for this formation of that reaction is minus 46 kilojoules per mole of ammonia gas that I produce. Okay, remember what is delta H? H is equal to the energy required to produce the system, to create the system, plus pressure volume to expand, to create a cavity, to create space in the environment for the system. So this includes, this part right here is pressure dependent. Depends upon the external. So why 1 atmosphere? Well, most of the times we do chemical reactions under 1 atmosphere. So it's a useful, convenient quantity. If you were working under 3 atmospheres or higher atmospheres of pressure, you would need to modify this delta H to find the actual delta H for the state that you're working in. We won't do that in this particular course. We'll assume that all of the reactions that we will work at will be under standard temperature pressure conditions. If you are an engineer, or if you're taking my thermodynamics class in physical chemistry, we would need to do this because of the fact that we'll look at chemical reactions at 1,000 degrees or very high pressures or low pressure type chemical reactions, in which case you can't use the standard states. We need to modify the conditions for the fact that we're not operating at the reference state. So that's again a point. So this table that I have over here, you can see off to the side of the screen, are tables from the textbook of different chemical compound, different precisely defined reference states. These precisely defined reference states are, if you notice, these are this sort of typical thermodynamic state of the system at T equals 298.15 degrees Kelvin, standard temperature and standard pressure. Ammonia is a gas, this is a gas, water is a liquid, this is a solid, this is a solid, carbon dioxide is a gas, methanol is a liquid, and this octane is a liquid. Okay, those are the standard states. Okay, again, it's convenient to define the standard temperature and pressure as 1 atmosphere in gases. The pure liquid or solid for condensed pure substances, again, at standard temperature pressure, because it depends upon, the phase of a solid depends upon the pressure. Again, in normal systems, we operate under the standard temperature pressure, and for things in solution, a 1 mole per liter, 1 molar quantity for substances in solution. That tells us the standard state. So if I'm looking at the standard state of sodium chloride in aqueous solution is a 1 molar solution of sodium chloride. Okay, that is the standard at 298 degrees Kelvin and 1 atmosphere of pressure. That is the standard state of sodium chloride, of a solution of sodium chloride. And again, for elements, the standard state is the form in which they exist under the conditions of 1 atmosphere and 25 degrees Celsius, or 298.15 degrees Kelvin is the standard state of the system. So so the nice thing is, in this particular case, is always given in terms of per mole of product when the product is in the standard state. And again, the reason for that is because this is an extensive quantity. Now, again, the notation is important to keep track of. This little 0 here denotes standard state. Different textbooks will use different notations in case you see different notations for this, but generally this is a fairly standard notation for the standard state. Other textbooks might use a symbol that looks like this for the standard state. For example, Atkins likes to use this symbol. I actually don't like to use this symbol because I don't have this in my so he will. I don't have a symbol for this on my computer. So he'll denote the reference, like the delta H, as something that looks like this with a little O/ type notation. But he's the only him and Brian Smith both use this notation. So it must be a very Oxfordian type notation. But those are the only two people that use this. Most people will use this little circle up here for the reference state. But again, it's just different authors will have different notations. Now, the nice thing about this is that if I do a chemical reaction under standard conditions, I can simply go back and use predetermined values of the delta H information for the different steps of that reaction. And so one strategy for doing this is, for example, to break everything down into their constituents. For example, the reaction of methane with oxygen. I can break it down. I can take methane. This is the heat of formation of methane, and the heat of formation of O2. Well, O2 gas is already in a standard state, and I can combine that to get these products. Okay, so step one, for example, is to break these things down, and it's a sort of a schematic diagram into its constituent elements. So a carbon and 2 hydrogen molecules. These 2 hydrogen molecules can react with these 2 oxygen molecules, because what is the to give me 2? Well, I have 4 hydrogens here and two oxygens, two oxygens. Well, I only need half the moles of these things, so I get a delta H for this particular reaction of this. I get this plus these oxygens to give me carbon dioxide. And this is but this isn't the mechanism for how methane gas is combusted. It doesn't you don't break it down in the actual chemical reaction. The actual chemical pathway isn't this. But it doesn't matter, because the only thing that matters in thermodynamics is where I start and where I end. What happens in between, thermodynamics can't tell you anything about. The only thing it can say is, well, if I use this path, I get this answer. If I use a different path, I get the same answer. So I can pick any path that I want, so long as I get the right answer at the end of the day. I will always get the right answer at the end of the day, provided, of course, that I add and subtract things correctly. But again, enthalpy, entropy, we haven't talked about entropy yet, energy are path-dependent functions. This fully takes advantage of that quantity or that property of thermodynamics. Okay? I can always add and subtract enthalpies of formation and multiply by whatever is required to get the chemical balanced equation. Generally, elements are not included in this because the formation of an element does not require, I mean, basically, we assume that the element is already in its reference state. It's already in its standard forms. I don't include elements themselves because unless a change in form is required. For example, going from solid carbon to diamond would require an enthalpy, because I changed. Diamond is not the standard state of carbon at 1 atmosphere and 298 degrees Kelvin. Carbon is the natural form. So again, if you reverse, its sign changes, the magnitude remains the same, the sign changes, and if you multiply the whole thing by an integer, or any number for that matter, you have to multiply delta H also by that number to take into account, because it's always in per mole of the amount of stuff that you produce. In fact, the easy way to do this is to simply look at the change in the delta H in the reaction. The standard delta H of the reaction, okay, the delta H of the reaction is simply, I look at the heat of formation of all the different kind of products and the number of moles of that product that's produced, subtract off, remember, products minus reactants, final minus initial, the delta H of formation of all of the reactants, and therefore that gives me the enthalpy of that reaction, the standard enthalpy of that particular reaction. Again, this is an easy way to calculate standard enthalpies of formation for a given system. So, for example, here we go. So if I have aluminum plus iron oxide, this is the thermite reaction, by the way. And if you want to see it, maybe we can pull up a YouTube video to watch the thermite reaction. This is a really fun but highly dangerous reaction. Don't do this at home. Let me just tell you how you do it, though. You need powdered aluminum and iron oxide. So how you do this reaction, if you were to be if you want to do some backyard chemistry during the COVID-19 quarantine, don't do this unless you want to catch your house on fire. Aluminum oxide, this is powdered aluminum, so take an aluminum chunk of aluminum, maybe your aluminum ladder, and just grind it down, and take a file and powder it. Make as fine a powder of aluminum as you can. Iron oxide is simply, you take steel wool plus bleach, for example. We'll do that and collect a precipitate. You get a red precipitate. Dry that out very nicely. Mix these together in the correct stoichiometric coefficients. 2 moles of this to 1 mole of that. You can figure out the mass ratio as well. By itself, it won't do anything. It's perfectly innocuous reddish powder until you activate it, light it on fire, and this will liberate an amazing amount of of heat. This will produce, during the course of the reaction, it will produce molten iron. So this is why it's so dangerous. Molten iron flies all over the place and eventually turns into solid iron. But you can cut cars in half with this stuff if you have enough of it. You can burn holes, you can weld with this particular reaction. So it's as I mentioned before in my lectures, there are multiple reasons why people go into chemistry. One is you like to blow things up, and this is one way you can do some pretty serious damage. It doesn't blow up; it just creates a lot of energy, and creates molten iron. But don't do that at home. Okay. Anyhow, powdered aluminum. Again, just if you go on eBay or Amazon and order 50 kilograms or a kilogram of powdered aluminum, you will probably get a phone call from Department of Homeland Security, because it's generally the people who would buy powdered aluminum are people who are going to make fireworks or run chemical labs. It's just not something you can get very easily, but you can make powdered aluminum by just with a file. It just takes a long time. It's not that I've ever done that before. Anyway, okay. Okay, so if I wanted to do this particular reaction, let's look at how much energy I need. I can look up. I know that the enthalpy of formation for iron oxide is this much. The enthalpy of formation for aluminum is this much. Aluminum and iron in their solid states are 0. So those are in the standard. Those are already in their reference state. So I go from aluminum at 298 degrees Kelvin, 25 degrees C. Iron oxide, 25 degrees C. This is in its reference state. This is in its reference state. The only thing I need to know is the enthalpy of formation of this and the enthalpy of formation of that. So what we do is the enthalpy of formation of this minus the enthalpy of formation of that. Okay, that's all we need to do. Enthalpy of the products, enthalpy of this guy, and these are all per molar. Notice that this is a nice reaction because I don't have to do anything. 1 mole of this, 1 mole of that. 1 mole this minus 1 mole of that. Very exothermic reaction. Minus 850 kilojoules. It's basically, like I said, molten. I won't do this in lecture because at least in our lecture halls, it's not set up for it. Maybe I can go online and let's look at thermite reaction video, and here we go. We can watch this really quickly. There we go. You can look this up as well. There we go. This is why it's sodium. See how that stream that's coming out the bottom of this? Maybe you saw that at the very beginning. That's liquid iron that poured out the bottom of this vessel before it broke in half. And inside of this is a pool of liquid oxygen. Now there's a better one that I like. It's on. Anyway, you can go online yourself and watch these things, and it's quite an impressive reaction to watch. Okay, so very fiery reaction. Okay, so yes. Okay, so there we go. So let me just conclude and talk about the use of enthalpy and why why thermodynamics is important to think about in terms of sources of energy, because what we're looking at are in order to drive a thermodynamic engine, you require either work or heat. Generally, a thermodynamic engine is a means of transforming heat input into work. We will find out that you can't do do that at 100% efficiency, you always lose a little bit of heat to the environment. But basically, every thermodynamic engine does the following. You have a hot source, you have a hot, you have a cold, and I have work. So I move energy from the hot source to the cold source, and I extract work. Okay, that is your basic thermodynamic engine. Okay, work is extracted. I transform heat. Heat is the flow. Heat in, heat out. Q in, Q out, and I get work that comes out. That is your basic thermodynamic engine. And so if this is a chemical reaction, then the heat that I would get out is the efficiency of this thermodynamic engine is ultimately related to how much energy in the form of heat do I get from a given chemical reaction that I can then transform into mechanical work, moving your car, moving something in the environment. This is your basic thermodynamic engine. So different chemical reactions will provide different amounts of heat, and that's important. So this is simply a graph over the side that is a now, one of the things I really don't like about this textbook, let me just gripe a little bit about the textbook here. What's the vertical axis on this? I guess this is the amount of sources per year of different quantities. So it gripes me very much when authors don't include axis labels. Always include axis labels. So in this particular plot, we have to guess, and I believe this is what it is that 1850, 91% of the energy source used in the United States was wood. People chop down trees, keep your house warm. Coal was the next. 1900, people started burning coal. This is part of the Industrial Revolution. Many coal plants. Petroleum and natural gas were certainly being discovered. Hydroelectric and nuclear sources. Of course, nuclear energy hadn't been discovered, but hydroelectric plants were being built through the 1900s, and even before that, hydroelectric was used. Not so much hydroelectric, but hydromechanical windmills and flour mills and water mills were used extensively for power. Not necessarily as electrical power, but certainly as other sources of power for ages. And then you can see in the 1950s and so on, petroleum natural gas creeps in quite dramatically, very easily transported and produced substance, and other sources also. Coal dropping down, maybe a bit of a recovery. Wood definitely dropping down. Very little of our energy sources is wood, and then finally hydro and nuclear, about 10%. So it's still. So what is coal? Coal is a mineral. I had a sample of coal. That is dug out of the ground. It's the transformed remains, mostly carbon remains of plants, mostly plants, cooked under immense pressure for a long period of time, and turned into mostly pure carbon. And most of this coal was produced about 25 million years ago or more, buried under tectonics and so on. And depending upon how long the coal has been aged, you have different kinds of coal. You have lignite, which is very recently produced coal, recently transformed coal. Subbituminous, bituminous, and anthracite coal. Anthracite coal, very high energy, hot coal. Okay, and it's 23% of the energy used in the United States. Now, the problem with mining anything really is that if you're a miner, your life is pretty miserable. This stuff is very dangerous to breathe. Most miners will die of mining-related injuries or problems. Mesothelioma, black lung disease, for example, simply breathing in this dusty rock for your entire life will kill you. And also it's a dirty form of energy. There's sulfur that is still trapped in the coal, mostly because of the remnants of the plants contain sulfur. And in addition to sulfur dioxide, it contains quite a bit of mercury that accumulated in the plants and animals that were mostly plants that contributed to the coal. So burning coal not only releases sulfur dioxide, which is when it's mixed with a little bit of water vapor, makes sulfuric acid. It releases a lot of mercury, in addition to some low-level radiation and other sorts of things. So in other words, what you're doing is you're burning up all of this stuff and releasing into the atmosphere all of these pollutants and all of these things that were trapped underground for eons. And unless you're very careful and maybe you can recover these, they go directly into the environment. The second thing is of course that it's well understood and well accepted at this point that carbon dioxide has had a dramatic effect on the overall temperature of the planet, and we can talk about the science and physics of this, but you can debate this all that you want. But pretty much for the last 100 and some odd years, we have understood that high degrees of carbon dioxide in the atmosphere will increase the temperature of the Earth. This is well-established science. There's no doubt about this. If you don't believe this, then you really need to retake this class at some point or another. And in fact, one of the most important things about this kind of a class is to give you the physics and the chemical knowledge that you need to know to understand this very important existential problem that we're facing. The problem with carbon dioxide is that it absorbs a lot of heat, traps heat in the atmosphere, and then radiates that heat at lower frequencies. Again, so maybe it absorbs ultraviolet but basically blocks the escape of infrared radiation heat from the atmosphere, and the atmosphere warms up. Now, like I said, this has been well known for well over 100 years. So one of the key figures in physical chemistry is a fellow named Svante Arrhenius, and he did a sort of back-of-the-envelope calculation one day and said that if you burn a lot of fossil fuel, you will eventually release a lot of carbon dioxide into the atmosphere, and that if you continue to doubling the concentration would lead to a 5 degrees temperature increase. It turns out his model wasn't too far off from more sophisticated models that were developed taking into actual things, volcanoes and solar events and all this kind of sort of thing. So his model is actually quite good. It's been back of the envelope calculation by Arrhenius. So pretty much fundamental physics, fundamental physical chemistry tells you immediately that loading the atmosphere with lots of carbon dioxide will increase temperature by quite a bit. Now, you might be off by a little bit, maybe a couple %, but it doesn't take that many degrees to really start messing around with ocean salinities and growth patterns and so on and so forth that lead to all of the the detrimental effects of climate change. Now it turns out that Arrhenius thought climate change might not be a bad idea, because he thought, well, maybe this would open up the uninhabitable areas in the north to being more habitable, and so he thought this was a good idea, and didn't realize that this was probably not a good idea, but anyway, so the graph that I have on the side is again from the textbook, CO2 concentration in ppmv, parts per million. I'm not too sure what ppmv is in this particular case, but I looked up my own information, and this is from the National Academy of Science, or rather from NASA, and this is the data that's really being plotted. This is the global temperature anomalies compared to over the last 100 years, and over the last 100 years we have increased our temperature by a degree Celsius on average. This is global average over the entire Earth. Again, it doesn't sound like a lot, but this is an average quantity, so it doesn't tell you anything about what's going on in different parts of the world. It also doesn't explain why is it today cooler than yesterday, and that this is an annual average temperature of the Earth. Sometimes you go up, sometimes you go down. Mostly you're going up. This is from the one of the original papers on climate change in Proceedings of the National Academy of Science, 2006. James Hansen and such. What's showing here are observations. Again, this is 2006. Station data and land-ocean data, and their models. Now, scenario A is like the worst-case scenario, where everything goes bad. Scenario C is the scenario where they envision dramatic reductions of carbon dioxide and active and profound attempts to decrease carbon dioxide in the atmosphere. And then the blue one is scenario B, which they took to be their best guess of what they thought their model should be parameterized to take into account most likely practices, and it's not quantitative in the sense that it doesn't give you exactly what's going on. But if you look at this data compared to that data, you see that we've reached this 1% increase that they predicted at about the right time, around 2020, and there's 2020. So their model is not too far off. Now, why is it there's so much noise? Well, it's a stochastic model. There's some averaging that goes on, and it's taking into account all sorts of different kinds of variables. But that's data, and that's a simulation. There are different kinds of forces affecting global temperature that can be accounted for in the model. There was a beautiful paper in Science magazine earlier this year that broke this down. This is from 2017 National Climate Assessment, and looking at different kinds of contributions to the global temperature. So volcanics, solar fluctuations, natural variability is this line down in here. So natural variability over the last 100 years would not account for the observed global warming. So consequently, if you eliminate everything else, human forces have caused global warming. Again, 1 degree over the entire Earth doesn't seem like a lot, but 2 degrees, 3 degrees, 4 degrees, especially in it's in the regions where temperature and or rather the freeze-thaw cycle depends upon this quantity. 1 degree change in temperature on average means that maybe your thaw is now in March rather than April, or maybe your growing season is longer in some places and shorter in other places, and different cycles are now thrown off, and allowing more predatory insects, for example, to move into an area, or maybe certain kinds of species to not exist in a given area. You can harness the wind. This is a source of energy, and so on. And of course, you can also look at this as different sources of fuel. Hydrogen to combustion to form water is another source of energy. Of course, the problem with hydrogen is that as soon as you start talking about hydrogen, and you see a picture like what I have over here, this is the Hindenburg disaster, 1934, I believe, where this Zeppelin, the Hindenburg, maybe 1936, was destroyed in a fireball that was caused all sorts of. I'm not even too sure what caused it, whether or not it was a thermite reaction, whether it was the hydrogen itself blowing up, or a fuel explosion, unknown. But basically, when it went to land, a spark went off, and boom. Surprisingly, not that many people died. In fact, in the footage of this, you see people running out of this inferno, and so it's. But anyway, the problem with hydrogen is, of course, production, storage, and transport of the material. You can produce it with natural gas to form carbon monoxide, and then the carbon monoxide can be sequestered. And of course, the problem of converting it from water, you would think, why can't we just do hydrolysis of water? Well, that actually takes energy, because water is a lower energy form of the water, of the hydrogen plus oxygen reaction. So you want to have something that's thermodynamically favorable. There's different ways that we can do this, and that are being considered. And the key is that maybe I can just heat up water and cause it to spontaneously decompose. Yeah, I could do that, but again, you have to think about it as in terms of heat in versus heat out. At what point do I require more energy to produce my fuel source than the actual fuel itself? So there's some trade-off that one needs to take into account. There's some problems and so on. But let's go back to enthalpy of combustion and compare hydrogen gas to gasoline. So this is so if I look at the combustion of hydrogen gas, it's 3 times as much energy per gram as gasoline. Okay, is that okay? Assuming this is true. So how much energy is required to calculate this? How much volume of liquid hydrogen is required to furnish the energy density contained in 80 liters, 20 gallons of gasoline? So you can figure this out, and using the information available, density of this is 0.071 grams per milliliter. I have this many grams per milliliter for gasoline, and I can figure out the mass of the gasoline. I know the mass of the hydrogen, and I would need 19,000 grams, 19 kilograms of liquid hydrogen to have the equivalent amount of energy of a gallon of gas, 20 gallons of gasoline. So the volume is 277 liters of gasoline, of liquid hydrogen, and that's a lot, 277 liters of this, and so that is of liquid hydrogen. That means you also need to have the capacity to store liquid hydrogen, which is not easy to do. So there's other alternatives that people are looking at, and so on. You can read through these yourself. Oil shale, ethanol, seed oil, and so on are all sources. And what makes a good energy source, as you can sort of guess, isn't so much just the energy that's released, but your ability to cart it around, the energy density. What is the energy per mole, and how easy is it to pull this stuff around? Makes for a good fuel. So anyway, the last part of this lecture was a little bit of a maybe social commentary, but how to think about what does it mean for how to think about different kinds of fuels for and think about different kinds of sources of energy. And it really isn't so much a source of energy; it's a source of enthalpy that we're interested in. It's the enthalpy of the material that we're interested in. The enthalpy of formation, the enthalpy of combustion, and so on are the key. Again, to reiterate all of this, Hess's law is based upon the observation, or not so much observation, but rather the mathematical statement that the change in the state function is independent of the pathway that I've taken. And so I can pick any reaction pathway that I want, sum up all of the steps that I used, and recreate the enthalpy of that reaction by looking at alternative kinds of pathways. And that is really the summary of Hess's law. And next time we'll pick up on thermodynamics, continuing on in chapter 7 and 8, talking about thermo and so on. It's and with that I will end, and keep working on your homework, keep working on your problem sets, and I hope you all are staying safe and COVID-19 free and not terribly insane already from your quarantine. So I'll post another lecture later. I can figure out how to get out of this. Stop.